Hi, I'm Michael. I'm going to be talking to you about some work that I've done over the last year with Joey and Tyson, basically adding a distance prior to some LISA data analysis. So to get us started, this is sort of a diagram of the LISA spacecraft. Fun thing that has happened in the news last week is LISA went into mission adoption with the ESA, which basically means the ESA has agreed to actually pay for the budget of the mission. So there is planned to actually launch in 2035. LISA is a gravitational wave detector, so we measure gravitational waves by looking at minute changes in length. LISA has 3 spacecraft that have these laser interferometer arms. This is a little garbled up here, but the arms are 2.5 million kilometers long. And what is being measured is, with interferometry, is minute changes in length to detect gravitational waves. The gravitational wave spectrum has a lot of different sources in it. This is a sort of a map looking at how strong the gravitational waves are on the y-axis, how much they're changing lengths. And you can see we're talking about relative length changes that are like 10 to the minus 16 to 10 to the minus 22 of a length. So we're talking about some really fine precision things. Over in the sort of slower, the slower waves, the lower frequency, we're talking about periods of years here. We have things that are supermassive black hole binaries. These are things that we pick up with pulsar timing arrays. Over here in the higher frequency, which is stuff you can actually hear, it's turned into sound. So we're talking about tens and hundreds of hertz. We have binary mergers, in spiral and mergers of usually double black hole systems or black hole neutron star type systems. In the middle, LISA is sensitive in the millihertz range. So millihertz, we're talking about hundreds of seconds, potentially 1,000 seconds of period. And we have a number of different types of sources here. We have the types of sources that would become LIGO sources, maybe in a few years, maybe in thousands of years, but they haven't gotten close enough to each other yet that they're doing their final in spiral into something. We also have things called extreme mass ratio in spirals, which is where you have like a stellar remnant falling into a supermassive black hole. The type of source that I'm going to spend most time on is galactic binary sources. So these are compact stellar remnants. They are usually a double white dwarf system or an AMCVN type source. They're very dim. So we've only seen dozens of these optically and generally just in the neighborhood around the solar system. So there's not a lot that's known about them. However, we believe that because there's been star formation in the Milky Way for billions of years, that there are lots of these things lying around, just that we can't really see them right now. You can have them be close enough to be transferring mass. So they're not, in many cases, they are very sort of like the simple binary system that you could model with gravitational waves, one of the simplest, but you can have mass transfer dynamics. And for LISA, we're expecting about something around millions of these to be in the Milky Way, but we're only going to be able to resolve like thousands of them. So these sit. This is the LISA sensitivity curve. So LISA can essentially resolve things that are above the curve. We're expecting that the unresolvable ones are going to sort of bump this curve up in this area, and that the resolvable ones are going to sit over there. So when we talk about galactic binaries and matching waveforms for galactic binaries, the parameterization that generally gets used involves the frequency of the gravitational wave and its time derivative. The time derivative is generally very small in comparison to the frequency. We talk about the amplitude of the gravitational wave when it reaches the detector. And then we also have the latitude and longitude of the source where it is in the sky, inclination and polarization, where inclination is the one that's hard to see from Earth and polarization is the easier one. And we also think about the phase of them. So each of these sources has these sort of 8 parameters that are observable parameters when we're actually observing them with the LISA instrument. So the way that we align what our gravitational wave model is with what we're actually seeing is we use Bayes' theorem, and we do sort of the standard trick where we have a posterior distribution. This is something that has a maximum at the best model, and my models are X, so X is just all of those variables together, and D is interferometry data. Now, LISA isn't flying, obviously, so currently we're using simulated interferometry data. There's a project called the LISA Data Challenge that all of the data for this project is pulled from. And essentially what they do is they simulate a galaxy and they simulate the response of the LISA instrument to that galaxy. And then they hand you a bunch of data that then you have to sort of back calculate the galaxy. So the ultimate upshot of this is that we actually kind of know the answer ahead of time when we're doing this, so we can sort of check ourselves in a way that we wouldn't be able to with real data. So this is the standard Bayes theorem trick where we get to swap these two at a cost of a ratio. The lower part of the ratio is the probability that we have the particular data that we have, so it's a constant factor, so we just ignore it because we're looking for maxima in this posterior. And then we call this one the likelihood and that one the prior. So this is the probability that the data matches the model, that we would get this data if that were the right underlying model. And P of X is the, before we do the measurement, what do we think the probability of getting those model parameters are? So for LISA has a bit of a unique problem when it comes to gravitational wave detections. So LIGO sources, there is a moment when it is inspiraling and merging. So there may be many, many systems in the galaxy that it is sensitive to, and even outside the galaxy, but those are not all happening at once in the data. You can slice out a part of the data and say this is one thing. For LISA sources, most of them are continuous. So we're hearing every source at once, and also the individual models for the sources are different. So when we have a source like galactic binaries, where we're expecting to find millions of them to be in the data, and for us to be able to resolve thousands, fitting those is very important in order to get at all reasonable values for any of the other stuff that we're expecting to see with LISA. And the phase space of our pi function, like how many parameters we actually have to stick into that X in order to calculate a posterior, is somewhere around 10 to the 5, thinking like 10 to the 4 galactic binaries plus 8 parameters per galactic binary gets you to about 10 to the 5. And that's just for the galactic binaries. I'm not talking about any of the other sources we set. And we also don't know how big that number is. We don't actually know how many sources are, so we have to figure that out as well. So the sort of basic answer to this problem that is currently being looked at is the global LISA analysis software suite. And I ended up working on sort of a component of this. So what we do is we do a global fit using a Markov chain Monte Carlo scheme. And the global fit sort of has multiple parallel searches going for individual different source types. And those source types exchange information about sort of what their current best modeling of the situation is as the Markov chains are being developed. So every source fit affects every other source fit. And you're exploring this very high dimensional space. The component I'm working on is called Galactic Binary Markov Chain Monte Carlo. It's GBMCMC. It's technically a global fit if your definition of global includes just a noise model and galactic binaries, it doesn't include anything else. But the sort of basic operation of this is you put in interferometry data, and it takes a narrow frequency band. We get Markov chains on that frequency band that have a probability distribution that is like the target function that we're looking for. And then we post-process them into actually a source catalog. And this is something that you would actually say, look at if you were trying to use this for astronomy. So it would actually say, no, there's a source at this location in the sky, and it has these parameters that we've measured with some error bars. So the parameterization that I explained to you a couple slides ago is this parameterization that's very focused on LISA and gravitational waves. It's not really focused on the underlying sources. So we talk about amplitude and frequency of the gravitational wave and how much the gravitational wave is changing in frequency. But the study of these objects is looking at what are their masses, how far away, like physically, where are they distributed in the galaxy, which includes a notion of distance, and then also what other astrophysical effects are going on. The other sort of weakness of doing the search in this parameterization is we talked about you have to come up with prior distributions for all of your model parameters, including amplitude here. So you have to come up with some physical model of the galaxy that and then determine what is your prior on what the amplitude of gravitational waves you're receiving should be. And right now in the software, this is it's slightly sketchy, I'll say, as to what the guess is there. So there's a desire to not use it. And there's also a desire to be able to output a catalog that is talking about masses and distances rather than talking about how loud is the source when it's viewed from Earth. And there are of course multiple different ways to do this, but the way that I'm going to talk about today is where you just move the entire search to the new parameter space. So that's what we're going to be doing. The mass parameter is this thing called chirp mass, which is, if you know about reduced mass, you can think of it like that, but for gravitational waves, it's a combination of the two masses. It has the dimensions of mass. This is an amplitude relationship, and you can see the amplitude is dependent on the mass and inversely dependent on the distance. And so this is basically like a brightness relationship. You get heavy stuff closer, it's brighter, it's louder. You put that same heavy binary further away, it's going to be dimmer. And similarly with making the binary light. Once we have distance and mass, it makes a little bit less sense to talk about the change in frequency of the gravitational wave, because we now know, if we're talking about something that has a certain distance and a certain mass, we now can come up with an expression for how fast that binary system is losing energy due to radiating gravitational waves. So instead, the parameter that we use is this f dot astro, which is essentially the deviation from what we would expect given the gravitational waves exist. So if you have a simple binary that's not doing any mass exchange, that just looks like sort of the textbook version of this, then this parameter is 0. But if it's not 0, and you can measure that it's far away from 0, then you know that something else is going on in that system that isn't gravitational waves. These are some plots to sort of get one's head around the distance and the mass relationship. So you can kind of see these are distances on the y-axis, and then I've got the chirp mass here, so heavier stuff's over here, lighter things are over here, and then I've graphed different essentially loudnesses of the gravitational wave here, so you can see that if you have something that's fairly faint, not very loud gravitational wave, it's either something that's pretty light and pretty close, or it's pretty heavy and pretty far away. And this is the same idea, but they're constant masses with the amplitude along there. Now this has introduced a degeneracy to my coordinate system because I've added this another parameter, but I've added one parameter and I'm still describing the same underlying system. So that's this sort of like the shape of that degeneracy surface in the phase space that we're working in. And this is going to become more important later. So yeah, this is a sort of an overview of what GBMCMC does. So GBMCMC actually doesn't make just one Markov chain. It does multiple Markov chains. We talked a little bit about it taking the narrow band frequency data, so it's only matching a really narrow band of frequency space. And then it's coming up with noise parameters and compact binary parameters that live in that frequency space that would explain those particular samples. The reason it's using multiple chains is because it uses a two different algorithms that depend on temperature. So it has this temperature parameter. Temperature parameter operates on the likelihood. And so if we go back to the likelihood, it takes the likelihood here to 1 over the temperature. And what that has the effect of doing is at higher temperature, the algorithm spends more time exploring the global phase space rather than getting stuck in some sort of local maxima. And as the temperature drops, you end up with to the 1 power, and you end up with your likelihood surface with all of its sort of pointy maxima back again. So two things are going on during a run of this. One of them is simulated annealing, which means the temperature of each chain is going down as we generate the chains. And then also parallel tempering, where all of the chains are at different temperatures and they're all going down together. But neighboring chains can actually swap their entire model with one another. So this mixing helps make sure that the chains spend the most time in the most fruitful areas of parameter space. The high temperature chain is able to discover a fruitful area of parameter space that will over time get passed to colder chains and get refined in a way that the hotter chain cannot. Within each chain, there's constantly this process of proposing a new point, where our point is these binary parameters. And there's noise proposals, there's fixed dimensional proposals, which modify just a single source, and there's trans-dimensional proposals, which are ones that add or remove an entire binary source. So these are sort of written on the same level, and I'm going to talk just a little bit about why we're allowed to do that. So this is the Metropolis Hastings algorithm, which is what I was just roughly describing, where what you do to draw your next model parameter is you draw from some probability distribution, and then you accept or reject it based off of some ratio that you calculate. It turns out that if you work through detailed balance with the Markov chain Monte Carlo algorithm, which basically says that it ought to be stationary once you've reached the chain having the distribution that you want for a posterior pi function, then if you use this acceptance ratio, it will have that property. We're not going to go through all this. There are many steps to get there. In a trans-dimensional model, we have to add a couple of rules to this, but it comes out very similarly. The rules that we add are essentially that you draw random numbers from some distribution that you have to define, and then your generation has to only use those random numbers plus your initial data point, which is the Markov property of the chain. It has to only depend on the previous data point. When you go down in dimensions, it's the same game, except you put primes in front of everything. And then the rule is that the XU vector, if you put that all together and smash that into one vector, and then the X prime U prime vector, those have to match dimensionality. So you say pick, for instance, we go up and down by dimensions of 8. So if you pick 9 numbers to go up in 8 dimensions, then your X prime is 16 because it now has 2 times 8, and you have to draw one number U prime to make it work, so that both of these add up to 17 dimensions. And with that, you can then go through a calculation with detailed balance, and you can get out this, which looks very much like what we had before. This Jacobian determinant is defined entirely in terms of derivatives of the H function. So the H function has to be differentiable, which in practice is not very difficult to make these functions have nice properties. In GBMCMC, mostly what we're doing is we're adding or removing sources, and this works out to be either the volume or the 1 over the volume of the Cartesian base space that you're adding each time you add a source. So this is sort of why we're able to treat fixed dimension and trans-dimensional proposals as kind of the same thing, because we just pick a different acceptance ratio and use the same algorithm. So in GBMCMC, there are a whole bunch of proposals that all needed to be changed in some way to alter the parameters, like we were saying. So we're not going to talk about the trivial ones. The uniform and the F statistic draw had some fairly large changes that needed to happen to them, as did the Fisher matrix. So I'm just going to talk about those. So for the F statistic and uniform proposals, the way that they compose a new data point is they both generate a random set of parameters, and then the F statistic proposal takes the additional step of using a pre-computed statistic over the data you passed in to essentially recommend likely frequencies and sky locations that are likely given your data. And so when we switch this, luckily none of these are the parameters that we're actually changing, so there's not a big deal with changing the F statistic. But when we change parameters, we now have to draw chirp mass from somewhere, so we're just picking a physically reasonable range of chirp masses, and it's just a uniform distribution. When we draw F dot astro, we draw it essentially the same way that F dot was drawn before, except we use the chirp mass and the frequency in order to alter the range. So we're picking something that's still physically reasonable values for F dot astro. The distance draw is a little bit more complicated. And distance is complicated because we're working in spherical coordinates, and there's more volume further away, it turns out. So we have sort of two ways we could draw the distance coordinate, the distance from Earth. We could draw it in a way that's uniform over all the volume, which would mean that we're tending to propose points that are very far outside the galaxy because there's just more volume out there than there is inside the galaxy. We could also choose to do it uniform in R, or say, okay, we're just going to pick a uniform value, but that's sort of biased with respect to volume. We end up picking points that are close to Earth. So what we actually do here is just take a linear combination of the two. In this case, A here is a small number, so we're taking mostly uniform over volume and then a little bit of uniform over R in order to get the algorithm to actually converge. And when you work that out, this is a normalized probability distribution that you end up with when you work that out and you remove the sort of the angular components. And then in the actual implementation, it's done with rejection sampling. Rejection sampling is happier when your function has a maximum of 1, so that's what the second equation is. So moving on to the Fisher matrix proposal. So how it works is it proposes jumps along eigenvectors of the Fisher matrix. Locally, the Fisher matrix is a inverse covariance matrix in phase space. It's an approximation of it. And the way the proposal is tuned, you end up with these jumps that are essentially 1 sigma, assuming your likelihood surface is Gaussian. And it turns out your likelihood surface, yes, there's some good reasons to assume that your likelihood surface near the maximus is somewhat Gaussian. And this is an illustration from one of Tyson's papers showing sort of what the shape of this is, where there's sort of multiple maxima that are near each other, where this is the maxima for the actual injected source. And those 1 sigma jumps tend to either jump you from one of these Gaussians to another one, or they jump you from the edge of the Gaussian more towards the center. So they generally improve your estimate if you're nearby one of these things. So I said we were jumping along the eigenvectors of the Fisher matrix. So my new parameter space is degenerate. So now when I go to invert the Fisher matrix to figure out what the eigenvectors are, you can't because it's singular. So the way that I went about solving this is I basically just pick 2. Every time we run the Fisher matrix proposal, we just pick 2. And then that is a reasonable basis set. And we calculate the Fisher matrix and jump along there. I spent some time sort of looking for ways to justify this that were more satisfying than it seems to work. I did find some information theory literature that was saying that you could think of the Fisher matrix as essentially a chart over an information manifold, and that what you were doing by changing coordinate systems was just picking a different chart. So that seems like it may be the answer, but I actually don't know what the answer is for why this works. So in addition to proposals, we have to come up with actually a distance, a prior on distance. So I'm going to start by talking about what the prior was on sky location, because actually there's a galaxy model just embedded right in it. So we start with a bulging disk model of the galaxy that is up top, this P galaxy, and when you graph it, it looks like, if you graph it in log space, it looks like that. And almost sort of see the bulge if you look really close, but it's a log plot, which kind of hides it. So this gets projected onto Earth's sky, and then we add an isotropic contribution in order to get a prior on a sky location. Now, the isotropic contribution is important because you want to have prior support in your MCMC algorithm for finding sources that are outside the galaxy, because those might exist. Yes, you want to bias toward things that are in the galaxy because you think most of these things are in the galaxy, but you also want to find them if the data says it's above the galaxy right here, where this is sort of looking along the galactic plane. So this is all how it used to work. When we're doing this transfer of from one parameter set to another, we stop using the prior on A. So that's good because we didn't really trust what was going on there. The P galaxy is a prior on distance, so that's a good start. We also need priors on chirp mass and F dot astro. The sort of made the same choices as we did in the proposal, where you just use a uniform variable and you just shift the F dot uniform distribution for priors on these two. There's probably ways to make more physically reasonable priors on these, but it's left for future work. So in order to actually evaluate P galaxy, we have to avoid anisotropy, which it turns out is fairly easy if you pick geocentric spherical coordinates. But there are other choices you could make here that don't work as well. We do need to add in that same isotropic contribution, and we need to do it in a way that avoids introducing a distance bias, introducing bias toward too far or too close. And we also need to evaluate this thing over a reasonable volume. So we're trying to come up with an isotropic contribution, so we can't really depend on the sky coordinates. We would like the far away parts to act like 1/r squared, because there's more volume far away and we want it to fall off in a way that doesn't introduce a whole bunch of prior weight really far out. But the problem with 1/r squared is it takes really large values near the origin of your coordinate system, so you can't use it because it would suggest that it would only provide prior support for things right near Earth. So what I ended up doing was coming up with just a Plummer potential that's smoothed over 10 kiloparsecs, and then doing the same sort of adding in of 10% of this. And you can see on the graph sort of what happens. You get prior support outside of the galaxy. You also get support for locations that are near Earth in the galaxy but are out of the galactic plane. And it also, you can't see it on the diagram, but it doesn't blow up near Earth. So that's good. As far as how far out we have to define this prior, because we do need it to end up normalized, and we have 1/r squared, so we do have to define an edge to what we're going to be working in. GBMCMC already has a detector noise model, so we essentially asked that detector noise model if you had a binary that's at the maximum of the mass range, it's 1 solar mass in chirp mass, and how far away can you put it such that when it's detected, it will have a signal noise ratio greater than 5. And that's graphed here. Sort of a couple of points about this graph. This sort of curve inward is because of confusion noise from other binaries. If you take the confusion noise out, it's a lot flatter here. And the fact that there's a mean here is because that's the point where the LISA sensitivity curve starts to go up with frequency. So as frequency goes up, LISA instrument becomes less sensitive. So this is why the distance that you're sensitive to that sort of fiducial source flattens out. And this uptick over here is a resonance in the detector model. The detector model that it uses is not a real detector model. It's like a Michelson-Morley one, so that doesn't represent an actual instrument response. And what I've got graphed here, the frequency is going along here. This is the cutoff radius in log. And then these are different observation times. So you get more observation time, you have to look sort of further out. If you're back at the enveloping, the not broken part of this power law, this is the formula you want. And it's just a fit to the detector noise that's kind of easy to keep in your head if you're trying to do this type of calculation over and over again. Talking about results, I've sort of made all these changes to this program, so these are sort of the results. I'm running on LDC's Radler simulated galaxy, which is one of their simpler ones. And we're going to start looking at detailed balance testing. So detailed balance testing is when you set the likelihood in your MCMC to 1, because you're trying to sort of take your data out of the equation and you're trying to figure out whether the proposals you've introduced are biasing you at all. So the expectation when you do detailed balance testing is that you're going to get back your prior, because your posterior is basically likelihood times prior, and you set your likelihood to 1. So you should be getting back your prior or something very close to it. And then we're going to talk about identification of sources and parameter funding for this new version of the code. So this is looking at sky location. Oh, wow, this is, yeah, projector's doing a real number on this one. So at the top, these are detailed balance testing before any changes, before any of my changes. So this is the sky prior that I talked about earlier, and this is what happens when you run GBMCMC with the sky prior and likelihood equal to 1, and you look at the posterior. There are some sort of overdense regions that's coming from the F statistic prior, because it does go over the data, and those overdense regions are actually spots where there's binaries in the data. And then a number of the other proposals sort of have the effect of smearing across more area and parameter space, and so that's why you see it kind of smeared out a little bit. This is the same thing, except in distance prior mode with all the modifications I was just talking through active. And you can see we're still seeing something that looks very much like a galaxy. The smoothing is the smearing is a little bit less, and that's because, as you'll see in the next couple slides, there is some smearing across the distance coordinate that I think is not really represented when we don't have the distance active. So this is another cross-check involving detailed balance, where I graphed the old amplitude prior, and on the left we have the old code, and on the right we have the new code. So the orange here, the orange smooth curves are the signal to noise ratio prior, which is how amplitude was proposed, and also how it was also the prior on amplitude when it was originally. And you can see that in detailed balance mode, this posterior basically looks like this prior. It's got the same shape, it's shifted a little bit, and that's because the algorithm does tend to prefer things that are higher amplitude. This is in the new version, you can see it's got a fairly different shape. It's differently located as well. Part of the reason it's looking at lower amplitude sources is because when you introduce this distance-based drawing method, even though I've sort of put my hand on the lever of like trying to keep it from exploring these really large distances, it still tends to spend some time there, and it spends a little bit longer converging. So a lot of what it's considering at any given time, if it doesn't have a likelihood to tell it, no, that's not there, is stuff that's further away in lower amplitude. So it does have this change. And it's nice that we can see that this is not the same shape as the SNR prior. If you're really looking closely at these graphs, you may notice that the SNR priors in these two graphs are not centered in the same place. That is because in order to convert the SNR prior into an amplitude, which is what this x-axis is, I have to integrate over the noise model that's being used in that run. And so because these are two different runs, the noise model was doing two different things. And so that integration has introduced a shift in this SNR prior. They are actually the same curve in SNR space. They're just different in amplitude space. If we look at the distance coordinate, this is the same type of idea where the blue curve is the galaxy prior, and this jaggy curve is the posterior. This is looking across every single direction we could be looking. So this is integrated across the entire sky. And that's part of why this doesn't, you'd expect this to sort of line up more with the prior curve, because we're trying to match the prior curve. But if we take a closer look, this is a little bit hard to see. Okay, I'm gonna use the stick here. So these, I picked specific integration regions. So for this plot, this is the same as the plot before, but I picked an integration region that's sort of right over the center of the galaxy. So this overdense region here is where the core of the galaxy is. And there's a little red box there that isn't really showing up great on this projector. But you can see that we're matching the prior a little bit more. There's some smearing of the samples around, but it's still sort of substantively matching the prior. This is a smaller integration region that's a little bit further from the core, but still in the disk. And we've got the same sort of thing going on. We've got a little bit of deviation at long distances. And then this is an integration region looking straight up out of the galaxy, out of the galactic plane. And we're also seeing that we're sort of substantially, the galaxy curve looks different in this direction because we're looking out of the disk. But we're seeing a similar thing where it does have some of the shape of the prior. All right, so source identification. This is a frequency and amplitude diagram for a very narrow frequency band. The little X's are the injected sources. They're the actual source locations that the simulated data was generated from. And then these are graphs of our posterior in frequency and amplitude space. And I think it's generating, it's got 13 of these. There's more than 13. You can see it's not detecting some of the less bright ones. But this is similar to the performance it gets without the distance prior. So we sort of haven't made it, I can at least say I haven't made it significantly worse at detecting sources, at least in this regime. I also did some additional runs trying to sort of tune the hyperparameters. So there's two things when we were talking about priors. There's the weight of the sort of isotropic piece of the prior that I'm artificially adding in. And then there's also the proposal, what's the weight of the uniform R coordinate piece? And I think on my slides, both of those are 0.1. It turns out that the best combination, which is the lowest amount of this sort of artificial push that I'm putting on it with both of these, but still gets good results in terms of finding enough sources in this frequency band where we're expecting to find 13 or 14 of them, is 0.1 and 0.2. And so just sort of this is kind of how another way to double check that I haven't put my finger on the scale too much with the way I'm designing these proposals. So this is what posteriors look like for a bright, it's really doing a number on these. This is what posteriors look like for a bright source in the 4 millihertz band. And this is actually source 2 in this figure. It's actually this one right here. And some of the features of this are, this can't be read, okay. This column, the horizontal of this column is looking at DFDT astro, which is the F dot astro, which is the number that we expect to be 0. And it happens to be 0 for this source, but you can see the posteriors are not that great. We're not really coming up with a value for that source. This chart here is mass and distance. And so you can see we've got this very clean line. That's what we would expect for something where we know the amplitude pretty well. And it's sort of illustrating the degeneracy. This sort of looks worse than it is. It turns out this distance is from about half a kiloparsec to about 3.5 kiloparsecs. So within our search volume, this is somewhat well localized, even though we do have some pretty significant uncertainty on like exactly where it is. And the other thing that's sort of nice about these is the sky location charts, which are here and here, are still looking fairly multivariate Gaussian. So we aren't sacrificing sky location, although at least this is we sometimes say that LISA has good sky localization, but it's really only good if you're talking about gravitational wave astronomy. It's not good if you're talking about any other kind of astronomy. This is what the posteriors look like for a sort of a mid-brightness source. This one is source 16 here, so it's this one down here. So we're not quite all the way to where we're losing detection, but we're starting to lose the ability to detect a source. And here we can see the same degeneracy going on, but we have some confidence that it's here. And this one, it's actually almost finding it in the right place. The error bars sort of look better on this one, but the scale is a lot larger. This distance goes from like 2 up to like 15 kiloparsecs. So our error bars are actually bigger on this one for figuring out distance than they are on the other one, even though it kind of looks like we've got a very small thing here. We're also still not really getting the FDT Astro. I think there's future work to be done here in terms of coming up with a more informative prior for F.Astro, and trying to see if we can use that to help sort of extract that value from the data, because I think it could be really useful. And finally, I also went and looked at different frequency ranges, looking at just how many sources were identified and how many iterations we needed to get to convergence. I haven't talked much about how GBMCMC does convergence, but it does a sort of an automatic thing where it looks at how much the likelihood is changing and makes a decision as to whether to end burn-in of the MCMC and actually start working on the chains. So there is some variance. If you're having trouble converging, this number will be bigger. But we're converging in what are reasonable numbers of iterations still, and detecting not quite as many as with the sky location. This lower one is with the distance prior. But in a lot of cases, we're having some comparable level of detection, maybe a little bit less. So that is all I have for folks today. And I don't know how overdue I am. But yeah, thanks y'all for listening, and I'm happy to take questions from the group or from Zoom. There is clapping.
I think Scott.
That's the wrong cursor. Too many cursors. Yeah, we could actually do Zoom first. If you hear me and you have a question, why don't you unmute yourself and start talking. Okay, cool. Take questions from the room. Merlin.
I just have maybe a basic question about GBMCMC, but since you can add sources as you go and do these changes, like how are you sure you're not like actually like it's nice when you have some simulated data set, obviously. But I guess like a worry out of you end up like overfitting your added sources when you're actually fitting like maybe some noise or some other usage parameter. I know obviously here we're just talking about.
Right, no, but this is a very valid concern. So this is not a part of GBMCMC that I spent a lot of time working on, but I did have to kind of understand a little bit of it just to make progress. And where this is addressed is in the catalog generation. It's in the post-processing step between when you end up with posterior chains and when you end up with catalog. And so The posterior chains, what you get out is every link in every chain has multiple sources. And there's no rule that says that, when source 0 in a particular chain is the same source as source 0 anywhere else, right? So you just have sort of a bunch of locations where you think there might be a source. And in the post-processing step, the catalog format actually links back to what set of posteriors it identified, because it actually has to use an algorithm to identify which things are sort of near enough to each other that we think there's a source here. There's essentially enough support in the posterior chains to say this source exists or it doesn't, and there's actually a tunable parameter there when you generate the catalog. You can, with subsequent observing periods, you can actually, and this is on my slides, but I didn't mention it. One of the proposals is actually used to take a prior catalog. This one is used to take information from a prior catalog and use it to inform a future search. So you would process your first 3 months of data, for instance, right? And you would come up with a catalog, and that catalog has links back to all of the posterior chains that it pulled from, right? If you use this and then you go generate another catalog, the new sources you can actually trace back to what were the sources in the prior catalog that were used as part of that catalog generation. So you essentially end up with this kind of interlocking tree structure of, okay, now we have 6 months of data and we don't think there's one source here, we think there's 2 sources close to each other. But you can look at that catalog and link back to the previous catalog where you saw one source. So essentially the answer to this concern is make the data available and then try to make that work. And I'm going to call on Tyson from the Zoom next. I know you had your hand up top.
Tyson's probably going to help answer this question.
Oh yeah. Go ahead, Tyson, if you can hear me.
Yeah, can you hear me?
Yes, we hear you loud and clear.
Great. Friendly amendment to that answer. So if the concern is overfitting because you have this freedom in how many source templates you include in the model, the reason we use this transdimensional Markov chain Monte Carlo approach in the first place is because that is accounting for the additional complexity you're adding to the model by including all these extra parameters, and you have to pay that price in order to include new sources in the model. So if you were to take that transdimensional Markov chain Monte Carlo Hastings ratio and make a whole bunch of terrible assumptions, you can sort of break it up into pieces that look like the likelihood improvement you get by including these extra degrees of freedom, and then this like Occam penalty that you pay by including all these extra degrees of freedom. So what the sampler is doing is it's sampling over all these different possible numbers of degrees of freedom in the model, and it's settling on those that are the highest probability, and then that probability includes a drag that you get for having extra parameters in your model. And then what Michael explained with the cataloging step of how then we put in some of our own little special sauce to decide what we think isn't just the right number of free parameters to have in the model, but what we think is the right number of sources that are represented by those free parameters. Take some extra little fiddling bits. But the leading order, safety check to make sure that we're not overfitting is by using this algorithm in the first place.
Thanks. Yeah, and I'm recalling that when you actually end up writing these, there's some temptations you have to sort of optimize away the MCMC missing the iteration, because some of these numbers end up really small when you introduce additional new parameters, and you essentially have to waste your time. Split. I think that's what you meant by paying the cost there. I mean, the algorithm has to essentially go for long enough that it can get to having more parameters.
But also just doesn't like having. So
Yeah.
Right. So you do fit a little bit of noise, but you're not going to just freely fit noise because there's a penalty.
Tom, you had a question?
This was awesome. All of my, I'm biased and I'm thinking about more massive things as well. But you didn't mention eccentricity, right?
No, I did not mention eccentricity.
Because I was wondering if, say, you get a source that is eccentric and having different emission because of that, is that going to be picked up as some effed up astro in this instead?
I would have to think about that more. I haven't thought a lot about how eccentricity affects this, and I also didn't spend a lot of time looking at the waveform model, so I don't have a good answer for you, unfortunately.
Yeah, I figure if your max chirp mass you're taking is 1, you could still end up with something where you can get like a neutral cell one dwarf, have some cake, have something.
Tyson is saying that eccentricity appears as harmonics in chat, so that may be the answer to your question.
There's other sets of frequencies.
Right. So that okay. So you don't have to worry about it. Nice.
Is there any hope of getting those two sources, those two dim ones, that last results?
I mean, there's essentially limitations to, like, just because the sources are there doesn't necessarily, like, just because they're there in the data set doesn't necessarily mean that there is a way to resolve them with the LISA data. They were just part of the data generation. And that's also going to be true. Like yeah, you can get your analysis as good as possible, but there is some limit to what's actually in the data to be extracted. All right. If there's nothing,
so it seems that choosing those priors can be hard sometimes and cause a lot of trouble. Is a fragmentation approach possible at all? It's kind of.
I have not seen a frequentist approach to this problem, but I did spend most of, like, the project lasted about a year. I spent most of the time looking at this particular approach to the problem, rather than trying to sort of like go broadly to other frequentist, like other types of approaches. What I do know is that just anecdotally, all of the global fit pipelines I have heard of use a Bayesian approach, and they also use a transdimensional Markov chain Monte Carlo algorithm. So maybe someone somewhere has some idea of how to do this that they're working on that is better. Like, you can't say that doesn't exist, but the ones that are built, that are operating off of, getting good results on LDC data, injected sources are all of essentially of this form using slightly different techniques. I also have I continue to have that question as I go through this, even though I haven't seen anything yet. Okay, I'm not seeing any other questions. So thanks everybody, and I think the next thing is the committee and me in the room. So the committee gets to ask me questions in private, and then committee deliberations. So thanks you all for.
Yes, the audience can let the speaker again. Thanks. You're dismissed. Thanks for coming.
Thanks, very lovely. Thanks, Michael.